that. Now using those equation, what we can do, we can model the system. Now if I show you directly how it looks like, it's quite complicated, right? So let's design something so that it will be easy for us to know what is happening in this model. And I've created a side block here, and I'll try to activate it, and then we can actually do something with our model as well. So equation, we are talking about the sprung mass. So the equation was quite simple. It had the sprung mass, it had the spring stiffness, and it had the damping stiffness. Now everything was mathematically leading to the final acceleration, which was the acceleration for the sprung mass, which is z as double dot if we write it in simple way. And then again, if I go to the equation, so if we see here the equation, it clearly shows that there are some mathematical symbols like addition, subtraction, and then there is division taking place. So we do the same thing in Simulink model. It's very simple if we start, like, it's the most basic programming language to program the model. So if we try to model it using the equation, it's quite simple. So we start with the sprung mass, and then accordingly we'll connect all the blocks which we had in our equation. And finally, you'll have something which has both sprung mass and unsprung mass. So this is how the final model will look like. And now, as per our controller design problem, we have to find out, like, okay, which controller should go with it. So normally let's check the response without any controller first. Like if I change the controller, and if I give only the input as this damping force which I have, which is around 1500 Newton, and if I take the road profile as a bump which I have modeled, what we can see is that our response will look something like this. If I run it, yeah, this is how our response will look like. Now, can anybody of you tell me, like, why it's not positive and why it's going down and negative? What is the reason? Okay, I'll tell you. So it's because of its own load. Gravity is acting on it right now, and it's always compressed. It's not. It's always in contact with the road, so you will have it in negative, and that this response is without the controller. So what if we put a PID controller in this? So let's do it. Like normally we check a lot of controls in this, but because we are directly considering the PID controller in this one, we are starting with the PID controller. Let's do with P controller normally, the proportional controller. This is the block in Simulink, and you can change the term as per your convenience. Whatever you want to try, you can change the term and see the response. So we'll start with P, and let's consider the response. The term should be 100. Let's take it 100, and we'll try how the response actives. Now this is another system which I had created. Again, it's connected to the force. Just force is not connected with the controller. So let's compare the response between without controller and with controller. So I'll just take this and let's see the response. So let's change this thing, and now when we see the final response, so what we see is that this one is with control and this one is without control, and it is actually having a bad effect on our system response, right? Using a P controller is not actually helping. It hasn't decreased the displacement, it has increased it, so it's not working. So accordingly, we are changing and adding maybe a PI parameter now, and we'll see how it affects. So let's keep it, let's give a general value like 5. Let's see how is the response. And what we see now, so again it's same. So the blue one is actually without controller response, and the yellow one is with control, which is weird, right? So it should actually help us reduce the displacement. So we can see that without feedback is actually performing better, though we have used a PI controller. Okay, and with feedback it is actually performing worse. We want this displacement to be near zero as much as possible so that our suspension travel is minimum. So what normally we do, we keep changing on testing different control strategies, and I had done it before, so I know, like, for this the integral value should be higher, and it should be somewhere around like 175,000, and there should be some derivative term as well. So let's take it just 1. So though it is a PID controller, but it can be considered as I controller because the P and D values are like very small or minimum. So now if we see the system response, it should work, right? So what we see here now is that our PID controller is actually going back to 0 and we are having minimum displacement, but without controller system, it's having like quite a difference and the suspension travel is in negative. So that is how we generally check the controller performance and verify like does it match with our requirement, does it match with what we want. So now the main question is, this is all done in model, right? How do I, what proof do I have? Like, will it work on my system? How should I check that? So this part is before you implement the code. You are checking everything in your model. Now why model? Because your equipment, your system, it's quite expensive to experiment. Autonomous systems, they come in like the values are in millions, and you don't want to risk the damage if you're not sure of your control strategy. So first you decide it, you plan it in the system using any software, not just Simulink. You can use any software, Scilog, tspace libraries, just to decide the control strategy. And then we move to implementing our control into the actual target link. We go for software in loop simulation, hardware in loop simulation. And I'll go back to PPT. So this thing is clear, right? Everybody got some idea that how we design control strategies using software. So let's tune the model. There are different ways. Okay, so normally you use your transfer function, which is your system model, and do it on paper. You can do that, which is like time consuming. You can again do it on real system or in model. And there are ways called Ziegler-Nicholas method, Tyler-Tubin method, which is like you keep observing the system response, you see the oscillation, and accordingly you will change your parameters here. The three parameters which you have, the P, I, and D. In our case, because our because our system is almost linear, we are not using non-variable damper. We can also tune it through the automatic tuning feature of Simulink. So normally you should not do it because in your actual system it won't really help, but this is the fastest way to tune your controller. So you just click on the tune button, and the best part of Simulink is it will give you all the plots which you want to determine the stability and the system response of your system in the model. And right now it's linearizing the plant, basically detecting like if there is any non-linear system in our model or not. And then once it has linearized it, if you are checking only for one road profile and you are getting some gain values, but if there is a big disturbance or a different road profile and your system is not performing the way you want, then there is a strategy called gain scheduling strategy, and then you have to use two different parameters as per those profile. That is what you can use if your input parameters are varying or the disturbances are varying, and you should be aware of those dynamics. It's a very good way to avoid, like using gain scheduling, you can avoid some kind of surprises from your disturbances, and you can be prepared to get the response you want. Yeah, so we are tuning the parameters only with respect to this disturbance. But if your control response very different when you're using another input, then yes, you have to tune your parameters. But if you are getting the same kind of response, then you don't need to tune those parameters again and again for different input. And it's quite unusual, for at least for this condition, it's quite unusual that you'll have different response for different inputs, until and unless it's like a very high concrete wall or something that you have to overcome while riding your car. So for this case, at least we don't have to tune it for different input parameters. So finally, when you have designed the model, you have decided what control strategy you are going to use it. You try to implement in, you try to analyze different responses. So the pothole profile, it actually looks like this, and this is the different responses you have, and this is the final response, the suspension travel, which we are trying to aim to reach 0 with respect to the pothole profile which we had. And after deciding the strategy, we go for the actual stuff, which is the implementation in software, implementation in hardware. We validate them on the actual stuff or through a hardware which emulates that response. And then we if everybody is satisfied, your stakeholders, you are satisfied with the controller response, then you go for the system level testings. So I would like to conclude the webinar.